this video is about implementation of vision transformer. So vision transformer, as most of you will know, that it is a paper that was named an image is worth 16 plus 16 words transformer for image recognition at scale. So this was somehow a groundbreaking paper that extended the implementation of self-attention and transformers to the vision models. So the implementation that I will show will not be a optimal implementation, rather a implementation for understanding how the blocks and the parts of vision transformer work. So my implementation will be mostly based on this diagram. Yes, there are other parts to it. Why the position embedding is added, why there is an extra learnable parameter that is called a CLS token, and how it is done and why it is done, how to visualize all of those things. It is also mentioned in paper, but there are some intricacies in learning why the position embedding and how it works. Those kind of things won't be discussed in detail here, but in the future videos or in the future sessions that or codes that I will share. More than that, we can visit the paper, and there are many stuffs in the paper that can be helpful understanding how and why it works. Other than that, we will directly jump into the code part. So the basic thing we can see from the diagram is it is named also a 16 cross 16 image as a token. 16 cross 16 image as a word, which is as a token. So how to do this? You can see there is an image that is uh, having a 16 for 16 patches, and the patches are then flattened and then projected into other dimensions. So first we can code this part. It will be a live coding session. So let us focus on step-by-step procedure. First we will see how the patching is done. So as an input, I am taking a 4 cross 3 cross 256 image, that is batch, comma channel, comma h, comma w, h and w are the 256 and 256, that the size of the image. Other than that, other than that, the actual problem with the initial implementation, not a problem, but a negative point of the disadvantage of the previous implementation was the input size of the image should be constant. If you're training a model with a 224 or 256 uh, size of image, you cannot infer or you cannot train a model on the same model on the different patches or different size of images. But that problem is somehow solved by a person called Ross Whitman, who manages the TIM library, that is PyTorch image library. So what he does is, in this part, he does a interpolation of position embedding and some other stuff also that you can do it later. That is a bit more advanced to this implementation. But the original implementation was supporting only 224 or the same image size that you start training with. So let's start with this patchy file. So what we'll do is we create a class called projection class, and we will start from there. Class projection. We'll require a self, and we will require how many patches that we will create, what will be the patch size, and what will be the embedding size. So don't get into this first. what we will see is how to find the number of patches. So number of patches is nothing but it is a total number of patches that can be created of size 16 cross 16 from a 256 cross 256 image. So if you see num patches, in our case, it will be 256 because 256 into 256 divided by 660, 256 patches. What embedding size will do, will flatten the images first. So if our image is 16 cross 16, the flattened part will be 16 cross 16 into the channels because we will have also having the channels access. So if you multiply with 16 on 16 channels, then you will have a flattened dimension of each patch as 16 cross 16 into 3, which will be 768. Let our embedding size also be 760. It doesn't matter. You can change the embedding size as a hyperparameter, but starting with that projection will be cell.num patches. We will also do a layer normalization. So, what will be the input? What will be the normalized shape of the layer norm? So, if you think like total number of patches, so I already mentioned, if the image size is B, comma C, comma H, comma W, and you are making it B, comma number of patches, then the last dimension would be H into W into C divided by six patch size 16 per 16. So this will be same. This will be same as sorry num patches. So this would be same as if you do it by yourself also. This will be same as patch size into patch size into P. So here I will mention because when I flatten the image, it will be of that shape. Now I'll do a nn dot linear. The nn dot linear is the part where you project the flattened patches into the embedding dimension. So we were changing the dimensions of the image from patches into patches into three to embedding dimension of your choice. So it would be patch size input, patch size, patch size, transform into embed size. Okay, into channels. Okay, channels. And then layer. There is also a topic why layer norm and not batch norm in VIT. That is, there are many subtopics of VIT and this implementation that are the questions are raised and discussions happens on those things, like why self attention, why it should be embed dimension, embed size, because the output will be embed size. So therefore, cell comma X. To see. Now comes the uh, important part. We will do a BS batch size, BCHW, X dot shape, BCHW, X dot shape, and then now I'm flattening the patches. So it was of batch size, channel, height, and width. Now it would be batch size, number of patches, and rest. So here the important point we should see is the number of patches should be always number of patches are calculated by dividing the dimension and the patch size. So it should be always divisible by the image size. If 16 and 256 is not divided by 16 plus 16, we should assert here like why it is not same. It should be same. But I'm not doing here for the simplicity of the implementation. But you should always implement in such a way that the image size that you are choosing should be divisible by the patches. Otherwise, it won't work. Um, then we will apply the first. Self, yeah, self, self, return. So we can so here is the image. Let's input search. So here is the image. The input should work here, and we should get a output of this batch size, comma num patches, and embed size. So let's see rejection layer. So num patches should be 256. Patch size would be 16. And embed side will be uh, let it be 768. It doesn't. We can put it 1024. We can put 192 um, as a hyperparameter. Actually, the parameters also have a VIT small, VIT large, and VIT huge, depending on number of layers and other things. So we can go to it later, but for our implementation, we can take it some values that fit the implementation. Okay. So we will put IM here and check the shape of the output. So it's working. We are getting batch size, number of patches, and embedding dimension. Now this part is done. Now we can directly write a class for vision transformer, our final model. Vision transformer. What the things you will decide? Just image, comma. So we will have an image size of 256 in channels. It's we can skip in channels if we want. It doesn't matter because We can implement for 1D also. So let's keep in channels. Let it be three. Three means RGB image. That's 16 as we discussed. Embed dimensions, embed size, 760. You can change it um, for your convenience. So num heads is for multi-head attention. If you see here, they have used multi-head attention. So multi-head attention is nothing, a simple attention of QKB that we will discuss when we are implementing. But the embedding dimensions are separated into multiple heads, and then the attention calculated, and then it is concatenated as a final output. So the dimension remains same after the multi-head attention, it does not change, but it's a multi-head attention is attention with separate with splitting the feature vector into multiple heads, and then finding the self attention and then concatenating the self attention to get your output. So it helps in certain ways because the closer the information, the correlation will be better. Like it will be useful. The far correlations might not be useful in model building. So that was one of the reasons. There are many reasons that you can create a content around. But any topic on this would take 1 hour or 2 hour for each topic about Bayesian embedding, about adding self attention. But there are much better YouTube content around it, like I can show you NYU SP21. So if you go to this part of the lecture, so there is no direct implementation of VIT or any BERT or any end-to-end transformer, but the concepts, mathematical concepts of self, cross, and hard attention would be clear from here. Other than that, if we go to the rotation and squashing part, this would help understanding how the neural networks are actually working, why the in a linear and why the non-linear activation functions work. So that is the main reason I will suggest this lecture series. But here we will do a simple implementation of the same of VIT. So we will create constructors. First num patches, image size, patches, squared. Similarly, cell dot embed inside and and cell dot num heads. The cell dot num heads. So we will create our first project. We will initiate our first projection layer from here. So projection layer. What was our this is our function. We will call it here. What are the requirements? It's cell dot num patches. This part you are already made sure that it's working. Uh, and patch size, okay, and embed size. Yes. So it's working. This is correct. And now comes the tricky and most intricate part of the what is the most confusing and intricate part of the ViT implementation. This is the patch and position embedding part. You can see here the class embedding, the extra learnable class embedding. Already everything is derived from the same X. As it is derived from the same X, so it will be WQX. Similarly, it will be WK of X. Similarly, it will be WB of X. If everything is derived from the X, then it's a self-attention because you are deriving every QKV from the same input. And then you do a simple Q dot K. What is Q dot K? Q dot K is nothing but having a correlation between two vectors that are learnable in some ways because their weight matrices are learnable. So what we'll have is a simple correlation matrix as dimension of the same matrices are n cross embedding dimensions e, and these as embedding dimensions a simple sorry k q multiplied by k transform. So this simply have a n cross n matrix correlation matrix. And every patch 1, patch 2, patch 3, patch 4, patch 5, everything will be having correlation with other patches. So how much patch 1 is correlated to patch 1, how much patch 1 is correlated to patch 2. So this will be having an attention score like this. But this part, this matrix is used in further calculation in VIT. So what they have done is they have simply created a learnable parameter class. What it does, rather than doing a n cross n matrix, they're adding a learnable parameter to this matrix that they're calling a CLS token. If you're adding a CLS token to the matrix, what will be the dimension of the matrix then? From number of patches, n is number of patches, then it will be n plus 1. So now we are having a matrix the dimension of n plus 1. What will be the embedding dimension? It will be n plus 1 comma number of the length of embedding. So this part actually learns all the features from the other patches and provides us a solution for other downstream classification and furthermore segmentation and other things. This is how the CLS token adds. I will simply do a CLS token of same dimensions and add it to the number of patches. So I will get a number of patches plus ones. And what is this position embedding? Those who are familiar with NLP or have learned transformers, they have heard about sine cos embeddings. But here, in the original implementation, they don't use a sine cos embeddings. They rather use a learnable position embedding of the same dimension of n plus 1, comma, embedding dimensions that we will see. Let us see that. We'll create a CLS token. NN parameter so that it is learnable parameter or simple torjot random. What will the dimensions? Dimensions will be 1. It won't be 1 because if it is 1, then you cannot add it to the batch size. It should be batch size. But when you are implementing in the init function, the constructor, you don't know the batch size. So we will replicate it for a number of batches and then we concat it. We will see that one. So one is the class token that will add. So the after concatenating it becomes number of batches plus one and self dot self embed and also position embed. Position embed. What's the damage? The damage is same as that of so it's done. Now we'll write a forward. I am leaving some space for the further implementation, but we'll check how it's working now. So my style of implementation is I will implementing and checking it by step if it's giving some bug and then moving forward with the other things. So we again we calculate the batch because the input size is PC BCHW. So first projection layer. Then we will add a selection. So see here, I will do a first contract based on batch size because I don't want a one. I want a batch size, comma one, comma embedding size for the concatenation. So I get a batch size, comma 257, comma 760 for this case. DS self dot CLS token. So it will stack nine. In which dimension will we concat? This will concat in dimension 0, which is the dimension of the batch size. Okay. Now I have a now I will do a x equal to dot concat. Same process, same thing I will do, but I will concat it the x. Let's say I should put it as a list or shuffle. And what will the dimension? Dimension will be across the num patches. Num patches and one, so it will become. So here it was b comma num patches comma embed dimension. It will become after this. So I will do a dimension equals to one because across this dimension, and it will become nothing but interesting. Then I will add a position vector. Position vector will be x plus so position. So I have learned a new thing in. I'm completely not sure about it, but the thing is, this operation, if you do x plus position of it, it would work. But if you do like this, it would give a backpropagation error in PyTorch. So somehow this thing calls a class in Python, and it when you are doing a backpropagation while training, it will show you an error. It will work in forward propagation, but it for my case it's not working for the back propagation. So I've tried it with this also and posted on the PyTorch community the same thing, that why x plus equals to 1 does not work, as it throws a in place error. Let us return. So it will not change dimensions, as we are only translating through the vector space. So okay. So this part I think everybody's somehow clear. I'm not giving the complete elaborated discussion on it, but this is how CLS tokens are done, and it's learning all the patch correlations. But the position embedding is a tricky part. Why? Why position embedding? Yeah. So what I understand and I've discussed with people that, and from bit of paper also, a uh, simple point. If you have a vector of I plus 2j cap, imagine you have an embedding dimension of 2. Here it is 7 state, but you have a 2. And there are also reason that there are many points we should keep in mind. This should be always a unique thing for every num patches plus 1. When you are doing a sign cos that is not a learnable parameter, is always unique position embedding. Position embedding. So you can search it and see it here. We can discuss it much later, but this is how it works. It's a very large n is a very large value that is used in this position embeddings. How it works? There are many blocks around it. There are also the new implementation like rope, position embedding, rotational position embedding, and there is a much more recent research on it and implementation of other position embeddings. But for now, we will go with the learnable parameter, and it should. There are many points that we should keep in mind. But one of thing is why it works is if you have a input of I plus 2j, and if you multiply a matrix, if you go to that video that I discussed about how the how the neural network works. So it is rotation and squashing. Neural networks, but rotation and squashing. Rotation is simply multiplying with the nn dot linear or having a training a model, and squashing is simply applying a non-linear uh, activation functions. Similarly, what is adding? Adding is simply translating with the vector space. If you add if you add 0.5 I comma j to this vector in 2D space, it will be translating to this direction. Earlier it was in this direction. It was more towards this direction. But now it will be going a bit more towards this direction. So this is what a position embedding does. Uh, I will create a video. I'm very interested in how it works. I will always obviously create some content around it and enhance my understanding about it. But for now, this works. Now we are completed this part, this thing with position embedding. Now we'll go further with transformer encoder. We do have a position. We have embedded patches. We have everything. Now we implement a multi-head. Implement this part, transformer block. Let's write transformer block class transformer block. What will be required is uh, For attention, multi-attention required heads. For multi-head attention, also the linear layers MLP required embed size, required hidden size for MLP layers, MLP multi-layer perceptron, and a dropout. Okay, now I will do. I'm doing everything on a Kaggle notebook because there is a GPU support and everybody can access it. But you can do the same thing on our local computers and Python scripts. And this should be. So what is the first step? This is normalization layer. Let us write now and dot. So again, what will be dimension here? It will be nothing but embedding dimensions. This because after this it will go into this. What will be the attention? We will implement attention. Attention. Now start with attention. I will give a very basic and understandable implementation here. It won't be the optimal one, but somehow with this implementation, I'm able to understand better how it works. As I showed you in this diagram and how the QKB are created, I will do it in a similar way rather than doing it directly. Obviously, you can refer to the other implementation. Other implementation, I will share it later, that are standardized and can be used in further projects and large scale deployments. So here comes the tricky part. So when we are actually we're having a embedding dimension of this size. Let us see our batch and n plus one, that is number of batches plus one CLS token and embedding dimension. So when I will do a multi-head, it will create multiple heads. One head, two head, n heads. We have a eight heads, so it will create eight heads. Okay. So each head will have a dimension as I will split the embedding features into multiple heads. Every head will have a n plus one into embedding by head. I will do it in the mouse. Okay. So it can be directly done. We can implement a simple attention here, it will work for sure. But this works better. In original implementation also, they have mentioned a multi-head attention here. We can do a simple attention here, and we can check the scores. We can remove the position embeddings, we can check the scores. We can replace the position embedding sign because we can check the scores. With multiple experimentation, we can change everything and we can do a model building process and we can change the model and we can get a very drastic changes. It can be negative, it can be positive, but it will be a very good experiment to do and how we can see the changes that are happening if you use multi-head or not, if you are using non by changing at the end of this implementation, we will be confident about changing the original implementation that we find in PyTorch image models, Hugging Face, or other other implementations of VIT and other changed like resonate residual connection VIT, scaled VIT, other types of VIT and segformer or other models architectures that are dependent on attention and this type of structures, encoder decoder structures. Mm, so here I am implementing what is mentioned. Yeah, different patterns. My way of doing is this uh, that I will create effective embedding size, and it will be embed size as I showed you, and divide by num heads. We'll store a num heads. Mhm. Ah, now simply we will create a Q matrix. What will be Q matrix? Q matrix will be a weight matrix that will transform our X and create a query input. So what will be embedding dimension? It will be effective embedding size. And we'll copy it and do 3 times. We'll change it to V QK. Then we'll find out. See, if you search self attention, let us search self attention is scale.py images. Images. This attention takes the input of QKV, and this is attention for this is softmax of this is called attention as correlations between the number of edges, and you can see a dimension under root dimension k. That means the dimension of key vector. And as our dimension of each of them are same, we'll put a root over of this embedding dimension and multiply with the value value vector. In implementations in NYUSP 21, I've seen many times they use a term called temperature. I will be using the same. They have reorganized every terminologies and other things in their lecture series, which helps us to learn better. So I will continue using it. They have also mentioned many things around it, and they have continued doing that. So I will be also doing this. But you can directly write D. It doesn't matter. We'll take a root of. So it will be n plus 1. Now if you take the shape of it, it won't be n number of axes. It will be n number of axes plus 1. So I'm writing n underscore 1. This, and we will create this and number of heights. So I will write a simple s is equal to s dot v. So earlier our dimension was ds, num touches this one, embed size. Now it will be ds num heights purchase plus one and ended. Nice. In that Q will be transformation of X using a learnable Q matrix. K will be the same from learnable K matrix. That is why they are called a self attention. It's everything is there from this X itself. Nothing is from outside. Everything is from self. That I have learned from that in our SP 21. That is the explanation they give. Here, what will be dimension? As we are implementing a software, let us do direct torch dot matmul first. Uh, Here it was query into key transform. What will be the transform? Transform will be for this matrix. This is our matrix. Our matrix is like this. Our matrix is n comma e, and it will be multiplied with e comma n. So we'll get a n cross n matrix. Understood? Here, q k dot transpose. This will be minus one first. And see, I am putting minus one first, and then num passes on this way divided by the temperature. Done. Our main thing is done. Now we will put this dimension minus one. Because our everything is done minus one. We will do dot dot mathmal. Now we will multiply it with vector v. Sorry, vector value. Vector, sorry, matrix value. So will be attention v simple. So here we should get the same as our input. Attention never changes the dimension of the vector. We should remember that. It should be same. Now we will concat it. I will concat it. We will leave it. It works. It works for me. Anybody who has done it and has a doubt or has a can ask me directly from my GitHub how it's working. But if some error is there in my implementation, do let me know. I am implementing what I've understood till now. And it can be obviously it can be wrong also. It doesn't. But what I am sure about is after this implementation, we know every part of our uh, ViT, and you can easily edit the other PyTorch image models and other trained ImageNet models as per our use. Now we have done attention. Now we simply implement attention. What is required? Num heads. Uh, This part and this part are done. Now this part and this part. Okay, we'll write a simple MLP for like MLP, including everything, including this. Display none. Then there's a linear layer. MLP, simple MLP will do. That you have seen a diagram of MLP million of times. Those are watching this video. And you have implemented it also. It's not of a big deal. We'll go to a higher dimension. Dimension hidden size. We'll have a simple nn dot value. So why I'm doing nn dot value is let us search value value activation function. So this is value activation function. One of the reason of using it is the original implementation. If you see the original implementation, ViT JAX Google. It was a paper by Google, so they have the original implementation in JAX. So it's not in PyTorch. So if you can, there must be some parts that we cannot understand for now here, but overall idea we can get it here. Add operation, how it is adding the operation embedding. We call it time steps here, which is we call it a number of processes. So in the MLP block, you can see they are using value. That is what n and dense, then value, then dropout, then dense. This is similar thing I'm doing. It might not be the same parameters or same thing. This is what I'm trying to do here. The input signal, then as the output was hidden size, here will be the input. And the output will be embedded size dot changing the dimensions and other data. Right? Done. Almost our everything from transfer blocks is done. Now we'll only write a forward for it. Also to mention a library that I have constantly referred from is ViT from uh, ViT PyTorch by Lucy Drains. I might be pronouncing it wrong, but this is the very the lot of implementations here. All the VITs. The VIT I was talking about is simple VIT with I might find it here. This is with the position sign pass embeddings, temperature, horizon, and you can look. Now you can understand these things easily after this implementation. I've also seen this implementation. So if you see my implementation, this implementation, there must be he is using rearrange. Rearrange, I feel it is almost same as you, but it is more deterministic nature. You do whatever what things you want to do. I am using almost the similar thing. I have used it multiple times. It's very easy to understand library. Other than that, uh, what people mostly use is Team. So this is go-to library for any image encoder, any image classification problem. You can change many encoders here and do many uh, do-it-yourself things for classification, segmentation, even obfuscation backbones, segmentation backbones, unit backbones can be created from here easily, and this is very helpful. Here you can see the implementation. The implementation first side because it has many things other than the implementation that makes it a library and usable. So it might be bit much more to understand than only the implementation. But it is a very good algorithm to directly plug in your image and use. But understanding the blocks and other things helps you to manipulate the model better and understand it and use it confidently and understand it. We will do at self non this is equal to self attention. X is equal to self MLP. Why x plus x? Why not only x? Because if you see the diagram, no, they have a residual connection. Why residual connection? That is a topic for discussion. Why position embeddings? Why layer norm? Why multi attention? This will discuss, and I will try to go further deep into the what I understand, and to better my understand, I will discuss it further as I said earlier in future sessions if I organize or if I do try to write a blog or anything. We'll continue doing that. And this L stands for number of layers. For now, I will only implement the transformer block. So done. We are done. We are implementing X and done. Again, if you do X plus X, it will give you error for sure. So now our almost everything is done. Now only we have to implement this parts here. See, it's only number four layers will be finished. I implementing a toy implementation here. We'll do a self dot layers. So how many layers we will have? Two layers of this block. So see how will I write it. I have my way of writing it. I put an sequential outside and I open the I put a list into it. This stands for opening the list. If you have, let me show you. These types of small things actually confuses many people how to do this and how to do that. You have a list and if you do a star, it will show you that. It's won't take. But the this thing now, this opens out the and the value. So it will be this. If you don't write this, it will work. I think it should work. No, it won't work. First list is not the submodule class. So if you open it, then it will work. But if you remove the brackets, what you are doing is remove the brackets simply. Right. So what will a layer? Our layer will be transformer block. This is called list comprehension. Num heads, embed size, hidden dimension. That's right. Then how many times? Or I, for or I in range and non-layers. Simple. And this one for implementation. It means that Now will be for every layer inside that layer. Layer. Our implementation is over. We have done the import part. Now we'll check if it's hidden dimension is not defined. Hidden size. Not hidden size. It giving our hidden size. Yes. Okay. I've done some mistake. I've done some mistake. What should we have done some mistake at? The mistake is num heads from one and this is embed size by 12 dot heights. Yeah, I've written here it is right, but I'll forget to. uh, it's working now. So what is our output here? After this, we have output the vaccines, num patches, question, and embedding, embed cells. Now our encoder is complete. We will have a decoder. What is our decoder? Our decoder is simply number of classes, num classes equal to let it be 10. We'll have a 10 classes. So dot classifier head equal to number of unique. Input is embedding size. Output is num classes. Ah, so you have this dimension. Now for the further classification, we have a CLS token having all the correlation. We will use only that. I remove this one. Which is, we can have this picture. So we had this n plus a matrix having CLS token, having all the features of all the correlations, learnable parameter, and the correlations and all of it. So we will use this vector CLS token, which will be the zeroth vector of all the um, zeroth vector of this, which is the attention matrix. As you have multiplied it with the value vector, it has become n plus 1 comma embedding size. Embedding size. So it will only take a zeroth zero position of it to get the CLS token, and we will do a further classification in that, and we will get our results. It works. Batches will batches zero, comma, everything. So here I will write get CLS token. Get CLS token. Dimensions DS, comma, embed size. DS, comma, embed size. And after the implementation of the head, it will become a equal to tell the classifier, tell the classifier. It will become DS, comma, 10. Let us check. Very good. It's working. Now what will I do is I will have a torch training cipher. I already have this PyTorch already has this training or classifier for beginners implementation. I've downloaded it here. Rather than writing it everything from scratch, we have only implement the model. So I have a notebook. I've downloaded the notebook, uploaded on Google, and I've also done it. So it's working. So I can show you. If you copy paste the model here. So what I've changed in that notebook is I have resized it to 256 for so that our model runs because our model depends on this message of 256. Other than that, I have not made any changes. I have put the vectors on the devices. I've put the models on the devices. So this is the same implementation, and I have put this parameter might have changed, but almost the same implementation. Right? It is on CUDA. Other than that, nothing is changed, and the inputs are in CUDA. So I can show you the data set is getting downloaded. It is done. Some expert list. Okay. You can see the dimensions here. Images. Initialized our model here. And it is equal to vision class and CUDA. You can change the parameter inside this init. It is define initialized right the loss function and optimizer. In a simple training without any validation, I'm doing it to take it my model. So this is not for a daily use for sure. For doing the implement using the ViT models and changing it, I would always suggest you to go to PyTorch image model again and again. Uh, Here you can see many implementations, all the models. Go to models, you can use the loss. Actually, try to use this loss and this um, optimization schedulers because I feel it is nice. The optimizers are very user friendly. Other than that, you can go to results, check results are image net dot results image net statistics. Results are image net. Very large. See, every model is there. EPA is there, Honest is there, BT is there. The interesting part is everybody uses VIT. Flip, see Flip, see SSL, see Dino. If you search Dino, Dino game, nice game, Dino model. Or if you search Sam, everything uses VIT huge, VIT large. So it has become a standard. So rather than going, it is always efficient to implement that rather than running after scores and everything. surely. So this is it's working. So surely it's working. Now that's it. Implement the model. And currently also have updated the GitHub. And I will surely mention the GitHub in the description below. That's it from my side. Thank you.